The equilibrium expression for a reaction can be written in terms of the molar concentrations. So we have the equilibrium constant with a subscript C, and take the products of the concentrations in a numerator raised to the stoichiometric coefficients, and divide them by the products of the molar concentrations of the reactants in a denominator raised to the stoichiometric coefficients. Now if the reactants and products are gases, it's more convenient to calculate the equilibrium constant in terms of the partial pressures, where we have the partial pressures of the products in a numerator raised to the stoichiometric coefficient on the partial pressures of the reactants in a denominator raised to the stoichiometric coefficients. And the equilibrium constant depends on the temperature, because you'll get a different set of equilibrium for a reaction at different temperatures. So in general, the reaction quotient has the same expression, but it describes the relative concentrations of the reaction species at any time, whereas the equilibrium constant describes the relative concentrations at equilibrium. And the reaction quotient tends towards the equilibrium constant, such that at equilibrium both constants are equal. And the same applies for the reaction quotient in terms of the partial pressures. And for substances with concentrations and partial pressures that are independent of the amount of the substance, such as solids and pure liquids, we don't include their concentrations or partial pressures when calculating the equilibrium constant or the reaction quotient. The equilibrium constant in terms of molar concentrations can be derived using the law of mass action, which says that the rate of a reaction is proportional to the product of the concentrations of each reactant. And it's also been observed experimentally that the equilibrium constant depends on the stoichiometric coefficients. So when equilibrium is reached, the rate of reaction in the forward direction is equal to the rate of reaction in the reverse direction. And therefore, if we divide through by the rate constant in the backward direction, and divide through by the concentrations of the reactants, this is equal to a constant, which is known as the equilibrium constant in terms of the concentrations. Now you can also obtain an expression for the equilibrium constant in terms of the partial pressures by using the ideal gas law. And if you divide through by the volume, you get the pressure being equal to the molar concentration by the rate constant by the temperature. And therefore the molar concentration can be written as follows. And from that, I'll leave it for you to substitute for the molar concentration of the products and reactants, and you'll be able to write the equilibrium constant in terms of the partial pressures of the gases. Write an expression for the equilibrium constant in terms of the concentration. Well, the equilibrium constant is equal to the concentration of the products in a numerator raised to the stoichiometric coefficient on the concentration of the reactants in the denominator raised to the stoichiometric coefficient. And we don't include the concentration of solids and pure liquids in the expression for the equilibrium constant.